Alright, so I received another question about a piecewise function. This time we have a function, define f of x equals, okay, I have it defined as negative 7x if x is less than or equal to 6. Otherwise, x squared minus 2x plus 5, so that's if x is greater than 6. Now the question is, identify any values for which f of x is discontinuous, and if there is any discontinuity, is that discontinuity removable or non-removable? Now, there is no particularly good way to immediately come to an answer. I will say that this is a continuous function. It's a polynomial. It's defined for all real numbers. It's going to be a smooth curve. It's a parabola. This is a linear function, which is going to be continuous. So over their respective domains, they are continuous. So the only question is, what's going on at 6? Are those two, is that curve and that line, are they connected? Or is there a gap between them? What's going on at x equals 6? So you really need to graph this. Now, you need to be able to graph by hand. Don't just use your graphing calculator and try to get an answer here. Use what you know about algebra and just about basic mathematics to graph this. Okay, so we have x and we have y, of course. Let's tackle the top first. So when x is less than or equal to 6, we use this function here, which is negative 7x. Now, negative 7x, just think y equals negative 7x. Okay, it's in slope-intercept form. It has a y-intercept of 0, so it passes through the origin and has a slope of negative 7. So that means we're falling from left to right fairly steeply. Okay, in fact, if you think about rise over run, you go down 7 units and over 1 unit. So somewhere down here, we go down 1, 2, 3, 4, 5, 6, 7, and over 1. Okay, so there is the line negative 7x. Now this says only if x is less than or equal to 6. So 1, 2, 3, 4, 5, 6. We only graph that line to the left of x equals 6. So maybe I need to go a little bit further. And then put a closed dot there to signify that f of 6 is down here. F of 6, and what's that point? This point is 6 comma negative 42. So of course I can't really draw this to scale because I would run out of paper. Okay, so the scale's a little off, but the picture will be accurate otherwise. So there's that point. And this goes on forever up and to the left, because for anything less than or equal to 6, this is our function. Now what about for values greater than 6? So not 6 exactly, but greater than 6. What happens there? We'll use this function. Now the question is, well, we know that's a parabola. It's a quadratic, so it's a parabola shape. But how do you graph it? Well, in the most basic way, you're going to make a T-chart, but there's some more advanced ways. For instance, what I would do is I would maybe identify the vertex of the parabola. Where is the lowest point of that parabola? Because we know if the leading coefficient of this quadratic function is positive, that it's going to be a parabola oriented opening upward. So the vertex is going to be the lowest point. That might give us a good idea what's going on. Now, how do you find the vertex of a quadratic in that form? You find the vertex by looking at negative b over 2a comma f of negative b over 2a. That is the vertex. All right, so what's negative b over 2a? Well, it's negative 2. It's negative 2. So 2 divided by 2 times 1. So the vertex of that parabola has an x-coordinate of 1, it looks like. Okay, so 1 is the x-coordinate. Again, that's negative b, so negative 2 over 2 times 1. So 1 comma f of 1. Well, 1 squared minus 2 times 1, so that's negative 1 plus 5 is 4. So the vertex is at 1 comma 4. So 1 comma 1, 2, 3, 4. So there's the vertex of this parabola. Now, if I was going to graph that parabola, I would then find a few other points. Let's evaluate a few other points. Like, let's say, make a t-chart. And let's just say x and y. So let's see. If the vertex is going to be at x equal 1, let's look at let's see, 0, negative 1, negative 2, maybe negative 3, and then let's look at, say, 2, 3, 4, 5, just to get an idea of what's going on here. So at 0, and we're only concentrating on x squared minus 2x plus 5, nothing else. Just concentrate on this right here. We want to see what this picture looks like. So at 0, that's just 5. Okay. At negative 1, well, we have negative 1 squared is 1, minus 2 times negative 1, so that's 1 plus 2 is 3, and then that's plus 5 is 8. Then we have at negative 2, we have negative 2 squared. Negative 2 squared is 4. Then we have negative 2 times negative 2 is 4 again, so 4 plus 4 is 8 plus 5 is 13. At negative 3, we have, let's see here, negative 3 squared is 9, positive 9. Then negative 3 times negative 2 is positive 6. So 9 plus 6 is 15, plus 5 is 20. Okay, so there's a few points for us. Now what about 2, positive 2 that is? So positive 2 squared is 4, minus 2 times 2 is, so that's 0, plus 5 is 5. 3, okay, we have 3 squared is 9, 9 minus 2 times 3 is 6, so 9 minus 6 is 3, 3 plus 5 is 8. At 4, we have 4 squared is 16, 16 minus 2 times 4, so minus 8 is 8 plus 5 is 13. And at 5, you have 25 minus 10 is 15 plus 5 is 20. So here's some nice points to get an idea of what this parabola looks like. There's a point on our parabola. We have the point negative 1 comma 8. So 1, 2, 3, 4, 5, 6, 7, 8. Negative 1. So there's a point on our parabola. We have negative 2 comma 13. So there was 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, up to 20. So we have negative 2 comma 13. So 8, 9, 10, 11, 12, 13. So we have a point about like that. Then we have negative 3, which I think 20 is the highest I went, about, oh, I need to go a little bit further left. Okay, so there's a few points. Let's go on to x equal 2 now. 2 comma 5. So 2, 1, 2, 3, 4, 5. I didn't grab 0 comma 5. 0, 1, 2, 3, 4, 5. So about right there. Then we have 2 comma 5. Then we have 3 comma 8. Okay, then we have 4 comma 13. So I hope you see, it's not a perfect parabola, but I hope you see what's going on here. 1, 2, 3, 4, 5, 5 comma 20. So I hope you can see there, that's a decent looking parabola. Now, here's the key. Connect with the smooth curve. So like this. Now, we don't want here, that's the parabola if we graph it over all real numbers. But we don't want that parabola over all real numbers. We only want that parabola when x is greater than 6. So I erase all of my work I just did, except for anything above 1, 2, 3, 4, 5, x equals 6. So my parabola is going to be going up like this. Okay? And the only part I need to keep is anything above 6. So erase everything. Okay? So no parabola. It looks just like barely a little bit of curve going up and to the right. Okay? Now, let's see here. What's going to be the, well, first of all, it's going to be an open dot there, because we're not going to use that curve to find f of 6. We're going to use this line to find f of 6. Okay, now what are the coordinates of that point? Well, let's see. If x is 6, it's going to be 6 comma something. All right? It would be, let's see, if we added one more down here, it would be 6 squared, so 36, minus 2 times 6, so 36, minus 12, okay, so 24. 24 plus 5 is 29. So here is a pretty decent rendition of the graph of f of x. So this is all f of x. It's not perfect here. As you can see, if you look vertically, I should have cut, in fact, I'll fix that. We should have put that about right there. Okay? There. So now those need to be lined up vertically. Okay. They're still not perfect, but they're pretty close. Okay? Because of course, to be a function, you have to pass the vertical line test. So it's kind of hard to do these sometimes by hand. Just try to be as accurate as possible. But what is the overarching point here? The overarching point here is that you have a continuous function here to the left, including 6. You have a continuous function going off forever, this nice curve up towards positive infinity to the right of 6. But what's going on at 6? Well, at 6, there's this huge gap here. There is no way to, and in fact, there's no way to bridge this gap. You might think to yourself, what if I draw a vertical line? I could bridge that gap. But if you draw a vertical line, that is like you added another piece to your piecewise function, that piece would not pass the vertical line test, because a vertical line is not a function, okay? Because there's a single x value being assigned to multiple y values, in fact an infinite number of y values, so that doesn't work. Okay, so what we have here is that at x equals 6 we have a discontinuity. That is, the function is continuous, not continuous at x equals 6. Because here what the problem is that the limit as x approaches 6 of f of x does not exist. So remember, we had our continuity definition, and it says that the limit has to exist. F of c has to exist. Well, f of c, I messed that up there. F of c does exist. F of c, in fact, f of 6 equals negative 42. We discussed that earlier. Okay, so f of c exists. So we don't violate that principle, but this is the principle we violate. The limit does not exist. Now the third principle is, if the limit does exist, it has to equal f of c. But since the limit doesn't exist, we don't even talk about that. So we have a discontinuity at x equals 6. Now what is the nature of that discontinuity? Okay, it's removable if we can somehow patch the situation. That is, if we have a hole, say, I'll just draw a mini picture over here. Let's say we have a function like this, where we have a hole here at x equals c. So this would be a rational function where you have like a quadratic on the top and a linear on the bottom, and you can factor and cancel some stuff out. So let's say you have that. You can plug that hole by simply redefining f of c to equal that point and fill that in, essentially. So that would be a removable discontinuity. But here, there's no way to patch the situation. Like I said, we might try to draw a vertical line and connect these two, and you would think, oh, I have a smooth curve. But you would have a smooth looking curve. It would be an equation. You would have a piecewise equation, but would not be a piecewise function because it wouldn't pass the vertical line test. Okay, so we say this discontinuity at x equals c is non-removable. That is, there's no way to fix the situation by simply redefining f of c. F of c is defined down here. If we redefine f of c up here, doesn't fix the situation. There's still going to be this big gap here that we can't bridge because there's no way to connect it with anything other than a vertical line, and so we can't fix it there. Okay, and even if it wasn't a vertical line, it would be completely changing the function. There would still be this big gap here again. So I don't want to mislead you thinking that if it's not a vertical line, that you could just connect the dots and be good there, because that would be a major alteration to the function. You can make a completely new function. It would have a piecewise with 3 parts, like we've seen in another example. But here, there's no way to bridge the gap. Since there's no way to bridge the gap, by simply redefining x equals c, then we say it's a removable discontinuity at x equals 6. So I hope this has helped. If you have any questions, always feel free to ask.